Okay, so thank you very much. So first of all, I would like to thank the organizers for the invitation. My name is Takasada Shibauchi from University of Tokyo, and today I would like to discuss the ultranodal pair state in sulfur-doped iron selenium superconductors. So this work has been done in collaboration with people listed here, and the main players are Kohei Matsura and Minbei Kyu and Yuta Mizukami in my group, in collaboration with the mirror cell measurements done by Tomo Uemura's group in Columbia University. I also acknowledge the collaboration with Tetsuo Hanagori in Meiken SEMS, who have done the STS measurements. Okay, so let me start with the general introduction on the different superconducting states with different gap structures. So this is the classification of the different gap structures. So you may have a fully gapped state in conventional S-wave case, and you may have point nodes in the Fermi surface like this, or you may have a line nodes or one-dimensional node like this. And in this unconventional superconductivity with nodes in the superconducting gap, the low energy quasi-particle excitations have energy power dependence of energy spectra. And if you apply a magnetic field, what happens is that you create superconducting vortices around which you have the supercurrent flowing like this, which results in the so-called Doppler shift in quasi-particle spectrum. And then you induce the low energy quasi-particle density of states. That is called the Borovic effect. So I think it has been established that you have three different kinds of superconducting states with different gap structure like this. So far, so good. However, very recently, there is a theoretical suggestion that you may have a fourth type with the two-dimensional nodes, or which is called the Bogoliubov Fermi surface. And in this case, you have actually the zero energy density of states, finite ones. And then, so this, to realize this very interesting superconducting states, the strong requirement is that you should have a time reversal symmetry breaking in the superconducting state. So let me explain this Bogoliubov Fermi surface. And this is a seminal paper by Daniel Altabel in 2017. So they have actually started with the so-called Bogoliubov-Dujan Hamiltonian, and they convert it to the antisymmetric matrix, and then they can mathematically define the so-called Pfaffian, P of K. And the Pfaffian in the normal state looks like this, which is actually non-negative. And Pfaffian equals 0 gives the information of the zero energy states. So in the normal state, you should get this Fermi surface in which the Pfaffian becomes 0. Okay? But if you go into the superconducting state, what happens is that this Pfaffian usually becomes positive. But in the unconventional superconductivity, you may have a Pfaffian 0, which corresponds to the nodes in the superconducting gap, or zero energy states. However, if they consider the superconductivity with broken time reversal symmetry, then they can find a solution that negative Pfaffian for some momentum space. And for example, in this case, you can find this torus. Within this torus, you should have a negative Pfaffian. So if you go from inside the torus and outside the torus, you can find a solution that Pfaffian becomes 0. That gives the Bogoliubov Fermi surface in the superconducting state. So this very interesting superconducting state can be considered as a spontaneous Borovic effect, which induced the zero energy state, even in the absence of magnetic field, if you have a broken time reversal symmetry in the superconducting state. Okay, so far so good. And then the group of Peter Hirschfeld have considered this iron selenium system, and then they considered the theoretical model to show that it may have a Bogoliubov Fermi surface. And here they assume that time reversal symmetry is broken in this material, which is actually given by this delta term in this Hamiltonian. delta determines the degree of time reversal symmetry breaking. And then they can find a solution that you may find far-field negative. Then topologically, the Bogoliubov-Felby surface may be topologically protected. And they named this state as an ultranodal pair state. So if you look at the electronic structure, in the normal state of iron selenium, you should have this kind of multi-band electronic structure. So you have a hole band in the center and the electron band in the zone corner. But in the superconducting state, you may find some parameter range that you can actually have the Bogoliubov-Felby surface, which are shown by blue lines. And that gives you the zero energy quasi-particle density of states. So if you measure, for example, specific heat, you can find the zero finite residual C over T. Or if you measure the tunneling density of states, so you can find the zero bias conductance like this. So that can be tested experimentally. So let's look at the experiment. So we have been working on this superconducting state of iron selenium. This is a very interesting material, but importantly, it shows the so-called electronic nematic transition at 90 Kelvin, and actually below which you can have a very anisotropic electronic structure. And you can also find superconductivity at 9 Kelvin. And this nematic transition can be suppressed by the sulfur substitution in the selenium site. And you can completely suppress the nematic transition by adding 17% of sulfur. And by looking at STM, you can actually find the position of sulfur atom, which shows no segregation, meaning that we have a pretty uniform superconducting single crystals. And if you apply a high magnetic field, we can observe the quantum oscillations, indicating that these crystals are pretty clean. So we have actually very uniform and very clean single crystals in a wide range of X. So this is a very important step to understand the physics of this material. So let's look at the specific heat first. So here is the C over T as a function of temperature measured by the so-called long relaxation calorimetry technique. So we use pretty small crystals, but we can measure the specific heat by high resolution by using this technique. And we can actually look at the superconducting transition and low energy excitation, but looking at the low temperature C over T. And by using this technique, we can map the electronic phase diagram, temperature versus sulfur content. And as you can see, this is the nematic transition temperature, and this is the superconducting transition temperature times T2. So meaning that in the nematic phase, we have actually TC of around 9 or 10 Kelvin. You can see this jump in specific heat. And within the nematic phase, we can see that at low temperatures, C over T is roughly linear in temperature, meaning that the superconducting gap has a strong anisotropy. But importantly, if you extrapolate this data to T equals 0, we have essentially no residual C over T within the nematic phase. However, if you go to the outside the nematic phase, which is in the tetragonal phase, we can see that a very large residual density of states in the specific heat data. And actually, in the T equals 0 limit, we have a significant residual C over T. We can also take a look at the STM spectra. And this is done by Hanaguri-san in Riken. And they can actually take a look at the so-called quasi-particle interference pattern, and showing that they can find the hole-like band dispersion like this, which shows smooth change as a function of x. However, if you look at the DIDB at low energies, within the orthorhombic or nematic phase, its DIDB curves shows a pretty similar structure with the V-shaped conductance at low energies. This is again showing that the superconducting gap is pretty anisotropic. However, if you go into the tetragonal side, outside the nematic phase, we find that you can see the very large zero energy conductance like this. So if you plot the zero bias conductance divided by the gap edge, which is shown by this green data, you can see that it shows up immediately when going from orthorhombic to tetragonal side. So there is a big jump. So only in the tetragonal side we have this very large zero energy DIDB. So from the specific heat data and tunneling density of states, we have shown that we have very large residual zero energy density of states in the tetragonal side of iron, selenium, sulfur, which shows very good consistency with the theory showing this Bogoliubov Fermi surface. But here is a key question. The key question is time reversal symmetry broken in the superconducting state of this material? Because this time reversal symmetry breaking is the very important ingredient to have this ultra-nodal pair state. So to address this issue, we have measured the zero field μSR, which is a very sensitive probe of the magnetic field inside the sample. So this can be used as a direct probe of time reversal symmetry breaking. So we first look at the iron selenium. So we use the correction of single crystals. And then here is a plot of the μSR asymmetry as a function of time. You can see the relaxation. And the red is in 20 Kelvin above superconducting transition temperature. And the blue is 2 Kelvin inside the superconducting state. And as you can see, we have faster relaxation at low temperature in the superconducting state. And from these data, we can extract the relaxation rate as a function of temperature. And we find that the relaxation rate increases below Tc, which is about 9 Kelvin in this case. So this increase of the relaxation rate indicated that we have small but finite static field appears just below Tc, which gives strong evidence for the time reversal symmetry breaking in the superconducting state of iron selenium. So we can repeat this kind of measurements in the tetragonal side of iron, selenium, sulfur, and here is the data for x equals 0.2, which is here, and 0.22, which is here. And essentially we see the similar effect, meaning that the temperature dependence of the μSR relaxation rate shows an increase starting from the Tc, which is 4 Kelvin in this case. So from these data, we conclude that the time reversal symmetry is broken inside the superconducting state, both within the nematic phase and outside the nematic phase. Okay. So this is the kind of summary of we have measured. The upper panel shows again the electronic phase diagram. So the blue point are the nematic phase transition temperature, and red superconducting transition, which shows the jump. And we have a lower Tc in the tetragonal side. And from the zero bias conductance measured by STM, which is shown by this brown data, and residual density of states from specific heat, which are shown by pink, they both show that actually zero energy states suddenly appeared when you enter this tetragonal side of iron, selenium, sulfur. And finally, we have also measured the transverse field μSR measurement. from which we can extract the superfluid density, 1 over lambda squared. Lambda is the penetration depth. And 1 over lambda squared is basically looking at the superconducting electron density divided by the effective mass, m star, which are shown by these red points, which shows a decrease if you go into the tetragonal side, which can be compared with the normal state of Fermi surface. So we have used the quantum oscillation measurements, and basically we want to look at the total carrier number divided by m star, which is kind of estimated from the quantum oscillation frequency f, which is proportional to the Fermi surface volume in the case of the quasi-two-dimensional material, divided by m star, which can be estimated from the temperature dependence of the quantum oscillation. And this f over m star is plotted by these blue dots as a function of x. And as you can see, in the normal state, Fermi surface is expanding if you increase the sulfur composition. However, in the superfluid density, in the superconducting state, shows a decrease in the tetragonal phase. So this means that, if you look at the Fermi surface in the normal state, not all the Fermi surface becomes gapped in the superconducting state, and there is some normal component left in the zero temperature limit. So this is actually consistent with the presence of some kind of a Fermi surface in the superconducting state. Moreover, the theoretical group have calculated the diamagnetic current response, which is related to the superfluid density in the calculation parameter range, and they have found that within the parameter range in which the Bogoliubov Fermi surface becomes stable, which are shown by this gray shade, the superfluid density have shown the substantial decrease from the original value, and which is actually consistent with our transverse field MESR measurements data. So from this set of data, we have actually concluded that we have obtained experimental evidence for ultranodal pair state with Bogoliubov Fermi surface in the tetragonal side of iron selenium sulfur. So this is our conclusion. But here is one open question remaining. The open question is that why does the suppression of nematicity drive the topological transition to this Bogoliubov Fermi surface state? So this is actually not clear at present, and we need further investigation to address this question. Okay, so let me summarize my talk. First, tetragonal iron selenium sulfur crystals exhibit unusually large low energy density of states, and USR results provide bulk evidence for time reversal symmetry breaking state, which is a requisite for a Bogoliubov Fermi surface or ultranodal superconducting state. And superfluid density, which is measured by the transverse field MESR measurements, indicates the presence of unpaired electrons consistent with the ultranodal state. And finally, iron selenium sulfur exhibits a topological transition to ultranodal superconducting state like this. Okay, thank you very much for your attention.
Okay, let me ask the question just.
Okay.
The time reversal symmetry breaking, as far as I understand, presumes the p-type pairing, right? And
well, not exactly. You can also have any symmetry, time reversal symmetry.
Any symmetry.
For example, S plus ID, for example, if you have the complex order parameter, that means that you can break time reversal symmetry.
So you didn't
and
see...
P-wave is also a possibility, P plus IP, for example, but there is another possibility as well.
Okay, in your data, when you trace the specific heat versus temperature, did you see any deviation from S-type?
Yes. Okay, so if you go back to the specific, okay, so inside, pneumatic phase, we see this T-linear behavior at low temperatures. And in the S-wave, fully gap case, you should have exponentially small, temperature dependence. So you can see the exponential temperature dependence at low temperature, but here we have T-linear behavior. And if you go to the this side, the terminal side, it's completely different from the usual S-wave case. In the S-wave case, you should have a very low residual value, essentially zero, and it shows an exponential dependence at low temperatures. But here we have a very large residual density of states, right? So this is an evidence that we have actually zero energy states appearing even at T equals zero, right? So this is evidence for some kind of a Fermi surface left in the superconducting state. So we argue that this is one of the evidence for the Bogoliubov Fermi surface.